We have seen the definition of measure and sigma algebra that give us the definition of measure space. In general, constructing a measure can be really difficult. If you recall what you did when you studied the Lebesgue measure on the real line, constructing the Lebesgue measure and the Lebesgue sigma algebra is really difficult. So starting from this lecture and the next, we're going to find ways that allow us to construct a measure on some sigma algebra from some very simple standard process. So in this lecture, we're going to talk about this definition of an outer measure, and this will lead us to the first big theorem of our class, the Carathéodory's theorem. All right, so let's start. So here is the definition of an outer measure. So here the word we're using, this word outer measure, well, first thing you need to know is that an outer measure is not a measure. It's a slightly different concept. So what is an outer measure? Well, it's trying to mimic the outer measure on the real line. So that's the key property it need to have is the following. So first of all, it's defined on every single subset. Okay, so here I define mu star on the power set of x, and it takes value between 0 to infinity. So again, I can allow it to take the value positive infinity. Well, you need to satisfy these three properties. So first of all, it maps the empty set to 0. That's quite simple. Second, you need to satisfy the monotonicity. So if I have two sets, E and F, E is containing F, then the mu star of E has to be less than equal to mu star of F. So say less than equal here. And then finally, you need to satisfy the sigma subadditivity. So if you have a collection, a countable collection of sets, then the outer measure of their union has to be bounded above by the outer measure of their sum. All right. So if a map satisfies these three properties, then we call it an outer measure. Well, of course, if mu star itself is a measure, then it's certainly an outer measure, but usually that's not going to be the case. We're only starting with something that's actually not a measure. And we eventually want to cut down on the power set of x to a set of something what we call the measurable sets respect to this outer measure. Well, before we go into the Carathéodory, let's start by saying outer measure are easily constructed. It's actually fairly simple to construct outer measures. Well, in this lecture, the main goal is to prove the following proposition. So suppose I have a collection of sets, let's say, let's give it a name, let's call it E, okay? There's some collection inside the power set, and it actually need to contain the empty set and the whole set. You can think about E as an algebra, or it can be just simply a bunch of sets that you can assign some value, all right? So now let's define some, suppose we have some value for the sets in E. So let's let function f from E to 0 infinity, just some function, okay? We don't require this function to satisfy too many conditions, but let's just say it maps the empty set to 0, okay? That's the only thing we require for this map, okay? Now let's, for every A inside the P of X, or you can say a subset of X, let's define a map. So let's define the mu star of A. Well, I want to define it as using the cover of A, using the sets in E. This is about the same procedure as when you first define the Lebesgue outer measure, where you define the outer measure of a set to be the open cover, the infimum of the open cover, where for the open cover, if you have a union of a bunch of open interval, you know how to define its value is given by this function f. So let me write this down. So I define the mu star of A to be the infimum of all the summations of these f of ei's. Okay, so here I going from 1 to infinity, where here the ei's are coming from this set E. So I'm basically using elements inside the C, and I want to cover the set A. So A has to be inside the union of these ei's. Okay, I going from 1 to infinity. So given a way to cover this A, I can find a summation of f of ei, and I would like to find the minimum value of the summation, and I assign this minimum value, the infimum, to be the mu star of A. Okay, so this is how mu star of A is defined. This is clearly well-defined number. I'm taking an infimum on a bunch of set, and you can clearly see, for example, if I take just E to be the entire set X, so A is certainly covered by X, so I'm taking an infimum over some non-trivial set. So the conclusion is this mu star is an outer measure. So this is essentially telling us there is a very standard procedure of generating outer measure. I'm just having a bunch of set E where I can assign some value, and then I using this kind of this covering idea to define a function mu star, and it's always an outer measure. So let's prove this proposition. All right. So we want to show that, well, we want to show it's an outer measure. Well, we just need to show it satisfies all three conditions. So first of all, mu star of the empty set. Well, to cover the empty set, you can just use the empty set to cover it, and the f of the empty set of 0, you cannot go anything below 0, so it is quite clear the mu star of the empty set is equal to 0, so that should be fairly simple. Second, you want to see this mu star is monotone, so let's take E is contained in F. It's quite standard. If you have an open cover of F, okay, then because E is a subset, then you know it's also an open cover of E. Okay, so let F to be a subset of unions of EI, where these EI are in E. Okay, so here I should say the E and F are both subset of X. They don't need to come from the E. Well, suppose you have a F which is covered by elements from this set BD, then you know that this cover also covers the set E. Okay, so here you also have, this is an open cover. Okay, so the mu star of E is certainly less than or equals to the summation of these mu's, well, not mu, but f, the f of ei's. All right. So for every such open cover of F, I know that mu star of E is less than or equal to the summation. So let's take the infimum on the right-hand side over all the all the covers of F. Then what do we get? Then we will conclude that mu star of E should be less than or equal to mu star of F. Okay, that's also fairly simple. Now I just need to prove the last one, which is the sigma subactivity. Okay, so let's change some letter. Let's don't always use E and F and get confused. So let's take, say, AN, a sequence AN. Okay, all of them are subset of X. Okay, so I want to show that. So I want to show that the mu star of their union, and going from 1 to infinity of these an, is going to be less than or equal to the sum of their mu star. Okay, so this is n greater than or equal to 1. Well, let's look at this inequality. Well, let's start by considering each of these mu star of an. We know from the definition we can find some E cover of each of these an, where the summation of this f of E is approximately equals to the mu star of each of these an. Okay, so let's fix epsilon greater than 0, and let's consider for each an. By the definition of mu star, we can find some good approximation, let's say E and I, where I going from 1 to infinity. This is everything is in this curly E, so that while the mu star of A, being the infimum of all such cover, will be less than or equals to the summation I going from 1 to infinity of f of E and I. And I can make sure that this choice of E and I is a good one, so it's going to be less than or equal to mu star of an plus this epsilon. Okay, let's fix epsilon for now. We'll make it smaller eventually, but let's keep it like here. And now what do we have? Okay, so we want to know what's the mu star on the union of these an. Well, each an is covered by these E and I, so if I take their union, I get another cover. Basically, I can use all the E and I's where I now let I and N both running from 1 to infinity. And that will give me, again, a countable cover using elements of E. So by the definition, so the mu star of this union of an greater than or equal to 1, that's going to be less than or equal to this particular cover. So this is the double summation on N and on I of F, E, and I. And for each one of these, I made it close enough to mu star of N. So this is equals less than or equal to N greater than or equal to 1 of these mu star of An plus an epsilon. Well, now you can see there's a problem. If I make the same epsilon for all n, well, then I'm adding infinitely many epsilon, then I won't get something nice. So I want to make this epsilon small enough, so I want to make it decreasing in terms of n, so that when I add all of these epsilon up, I get something still small. So a standard way, as you probably already know from previous courses, you just take epsilon over 2 to the n. So because the infimum, you approximate E and I to an, you can choose epsilon over 2 to the n. That's a fixed number, so you can do that. So now let's change this to 2 to the n. So this one will be equals to, let's take all the, sorry, this shouldn't be a mu star. This should be a f. So here is an f. So I can sum all the f of an up, so n greater than or equal to 1, and I can sum all the epsilon up. I will get an epsilon in the end. Okay. So this tells me that the mu star of this union is less than or equals to this. Well, now each of these summation I greater than or equal to 1, if I fix an n, this summation I know is less than or equals to mu star of an plus an epsilon. So because each one of them is less than or equal to that, I can certainly do the summation is still less than or equal to that. Now look at this summation. Well, you may notice there's a problem. I'm trying to take an infinite sum of epsilon. That won't be nice. It will diverge. So now let's go back to our choice of this ENI. Well, we can certainly make a little bit more close to this mu star of AN. So this is a standard trick in analysis, is that when you try to add uncountably many small things together and you want to make it small, you divide it by 2 to the n. Okay, so you let for each n, you make it increasingly closer. So you fix an epsilon, but for each n, you make it epsilon over 2 to the n. And now this is over 2 to the n. And this summation now is nice because you can break it into the mu star part. You sum all the mu stars of AN, and then you sum all the epsilon, that will give you the epsilon back. Now what do we have? Well, let's see. So we have the mu star of their union is less than or equals to the summation of their mu star plus an arbitrary term, epsilon. So this is arbitrary. So certainly, because it's arbitrary, you can let epsilon goes to 0, and you can make the conclusion that this mu star of this union of AN is less than or equal to the summation mu star of AN. So here are both n greater than or equal to 1. All right, so this basically proves the last property, the sigma subactivity. So this proves that mu star is an outer measure.